Okay, let me start. I've uploaded exam instruction and the announcements over here. So this is a table for the chi-square distribution and the normal distribution. So I think you already know this from the previous courses, the probability and the baby statistics class. So I just skipped that. So I will put that into there just in case if you need. And the final exam time and date are 3:30 to 4:45, Thursday next week. And the structure, the instructions are almost the same as the midterm exam, so I'm not going to repeat that. But the difference is the coverage will be all the contents covered throughout this semester, and out of the 100%, 20 to 40% of the exam questions will be the problems from different problems from the contents before the midterm exam, and 60 to 80% of the exam questions will be the contents that we've learned after the midterm exam. And before starting the exam, I think you can print the tables, so you can prepare it before starting the exam. And the difference, another difference is the handwritten formula sheet. So in the midterm, you have the one-sided, and now you can have the double-sided. So you can use this double-sided paper. And these are the some incentives for the final exam. I think I've already talked about it. So if you get the top score, then you will get A plus, whatever your midterm score, whatever your homework score. So if you get the top in the final exam, then you will get A plus. It's because this covers all the contents we've learned throughout this semester, so it's reasonable to give some more incentives. So similarly, if your final exam score times 80% is greater than your current midterm score in terms of the percentage, then your midterm score will be changed to this in terms of the percentage. Okay. And instructions here are the same, but you will need to print the tables, and you can use the two-sided, double-sided handwritten formula sheet, and the others are the same. And at this moment, I'm not sure how many questions will be there, but the length of the exam might be probably shorter than the midterm exam, so that you have enough time to think of the exam questions, each of the exam questions. Okay. And the homework keys, or all the homework keys are uploaded here. And the homework 5 key, yesterday I've uploaded homework 5 key by mistake. And this homework 5 key is a kind of updated version. So if you checked the homework 5 key yesterday, then you may need to check this again. And this homework 5 will be the last homework, and so including this extra homework. So you have total 6 homework, and there is no more homework. Okay, so what you need to do is just prepare the final exam. It will cover everything we've learned throughout this semester. Any questions? 대면으로 시험 보는 사람도 테이블을 출력해야 되나요? 네, 대면으로 보는 사람은 테이블을 나눠드리겠습니다. 그 전에 한번 그 인원을 대충 파악을 해볼게요. 시험 문제부 리프린트하고 테이블 나눠줘야 되니까 어느 정도 인원 수가 대면으로 올지 확인이 안 돼서 간단하게 할게요. 만약에 대면으로 시험을 봐야 된다면 yes를 해주시고 집에서 아니면 다른 공간이 있으면은 no를 답해 주시면 돼요. 설문조사 시작할게요. Please take the survey right now about the testing the final exam. So if you're taking the final online, say no. And if you need to take the final on campus, click the yes. 교수님, 과제는 6개가 전부 성적에 반영되는 건가요? 아니면 제일 낮은 성적의 과제 1개는 반영이 안 되는 건가요? 네, 홈워크를 보면 6개가 있고 그 중에서 5개가 레귤러 홈워크이고 하나가 엑스트라 홈워크이죠. 엑스트라 홈워크는 제가 말씀드린 대로 그 토탈 100% 뒤에 추가로 붙는 거예요. 이건 절대평가를 할 때는 이런 점수가 있으면 이게 추가로 붙는 게 도움이 될 것 같고, 그럼 이제 5개 홈워크 갖고 이제 레귤러 홈워크가 될 텐데 이 5개 홈워크 중에서 제일 낮은 점수는 제거되고 나머지 4개의 점수를 갖고 홈워크를 집어넣을까요? 25%인가 30%인가 막 그게 있죠. 20%인가. 그래서 홈워크 5개 중에 하나가 조합되는 거고 엑스트라는 그냥 엑스트라라서 이거는 고려가 되지 않을 거예요. 이건 그냥 따로 엑스트라로 그냥 따로 추가하는 걸로. 그리고 시험 온캠퍼스 시험이 지금 대충 한 12명이요. 13명. 파이널을 집에서 볼 수 있으면 집에서, 네, 이 정도 인원이면 괜찮을 것 같네요. 그 인원수가 공간이 넓지는 작지는 않으니까. 그래서 만약에 대면으로 시험을 보게 된다면 뭐 계산기, 펜 이런 거는 본인이 준비해 하셔야 되고, 그 답안 쓰는 그 블랭크 페이퍼는 저번처럼 나눠드릴 거고, 테이블도 같이 나눠드릴 거예요. 그리고 계산기, 펜, 그리고 그 포뮬라 쉿, 네, 포뮬라 쉿 이렇게 준비해 주시면 네, 되겠습니다. 네, 대충 파악 완료됐고, 네, 설명 감사합니다. 그러면 다음 주 목요일 날 3시 20분쯤부터 준비해서 3시 한 27분쯤에 문제 업로드 될 거예요. 저번처럼. 그럼 그때부터 문제 풀어서 4시 50분까지 업로드를 마치면 될 거고 4시 50분이 지나면 업로드가 안 될 수 있으니까 그 시간 전에 해주시면 되겠습니다. 그러면은 앞으로 남은 시간이 저희가 지금 오늘 그리고 목요일 그리고 다음 주 화요일이 있죠. 근데 그 저희가 화목 수업이다 보니까 따로 거의 빠졌던 건 없고 유일하게 한번 빠졌던 게 그 시험 전에 중간고사 전에 한 번이라서 15주 이상은 이미 충분히 채운 것 같아서 다음 주 화요일도 시험 준비를 위해 그냥 시간을 수업 이렇게 미팅은 안 하는 걸로 하고 질문 있으면은 그 오피스나 미팅 그 이메일로 해주시면 될 것 같아요. 그래서 이번 주 목요일 금요일까지 수업을 하는 걸로 하고 다음 주는 시험 준비로 하고 16일 날 시험을 보도록 하겠습니다. 네, 그리고 그 렉처 슬라이드 하나가 더 올라왔는데 거기에는 시험 좀 더 프랙티스 프로블럼 좀 더 풀어드리려고 거기 올려놨고 그 9일 이번 주 목요일까지 그 문제를 다 풀 수 있을지 모르겠지만 뭐 다 풀게 되면 다 푸는 거고 다 못 풀게 되면은 따로 뭐 더 답을 드리진 않을 거고 어차피 연습 문제 같은 거라서 그 질문 있으면 이메일로 하면 될 것 같은데 시간이 지금 뭐 미리 올려놨으니까 9일 날 오기 전에 한번 문제를 다 미리 어느 정도 보고 그냥 머릿속으로 어떻게 풀지 생각만 해보고 그래 주길 그러면 좋겠네요. 그러면은 목요일 날 제가 따로 문제 읽고 뭐 풀어보는 시간 안 갖고 바로 문제 풀면 되니까. 그래서 목요일까지 그 슬라이드 올려놓은 거 한번 풀어보시면 좋을 것 같네요. 목요일 날 하는 문제풀이는 따로 시간 안 들이고 그냥 바로 답으로 풀이를 빠르게 요약하는 걸로 할게요. Okay, so let's start the lecture. So we had a few more questions left. So let's start here. So we have the random samples following the normal random variable, and it asks find the sample size for testing this and find the UMP test. Against this, you can see this is a left tail test. So when you look at the UMP test, what you need to do first is looking at the likelihood ratio. So you can apply the Neyman-Pearson lemma, so they provide the most powerful test. Okay, so first thing you need to look at is when you have the NP or UMP, you start from the likelihood ratio. So 2 pi sigma 2 pi sigma square to the minus n over 2. So e to the minus 1 over 2 sigma square 3 square times summation of I equals 1 to n xi minus mu 0. So let me rewrite this as theta 0. So let me rewrite just theta. So theta 0, which is 20 square. So this is the likelihood ratio for the null hypothesis. Likelihood of the null hypothesis and likelihood for the alternative. So e to the negative 2, 3 square. Summation of I equals 1 to n xi minus theta square. And then these are canceled out. The remaining term will be the exponential part, e to the minus 1 over 36. The xi square part will go, and 40 square and theta square doesn't depend on x, so I'll just ignore, and then what we have is just summation of xi. So minus 40 summation of xi theta minus 20 times 2 I equals 1 to n xi, and multiply some positive constant in terms of x, right? So C includes e to the minus 1 over 36 times 6 sigma, like 40 square or theta square, these terms will be there. And the NP lemma tells that here the ratio on our test is the left tail test, and if you look at the ratio summation of xi, so LR. Let's see. If theta is greater than theta 0, so this is a theta 0. This is negative, so this is monotone decreasing. So the likelihood have the monotone non-increasing emitter. So when we talk about the increasing decreasing, we consider this guy. The alternative is larger than the null hypothesis. So given this, if this is non-increasing with this test statistic and this statistic, and we say this is emitter property, right? Then the Neyman-Pierce lemma tells that the most powerful test is if theta equals theta 0, theta is greater than theta 0. The test rejection region will be a form of T of x is less than something, greater than something, sorry. Right, so this is large, means the likelihood ratio is small, so we reject because the likelihood in null hypothesis is too low. And if your test hypothesis, your hypothesis are in the other direction, the left tail, then the rejection region has a form like this. Right, so the rejection region is this. If sum of xi is less than something, the rejection region should have the form like that. Okay. So given this is normal random variable, we know summation of xi or x bar, we know this theta over the 3 over square root of n, right? We know that normal random variable when theta 0 or 20. So you can use this to figure out the critical value, this critical value. Okay. Okay, so the rejection region will be such that x bar minus 20 over 3 over square root of n is less than or equal to level alpha. Level, what is the level here? So it says that probability that when theta equals 20, which is theta 0, x falls in the rejection region is 0.05, which means it is a level 0.05 test. So z 0.05, and this is a left tail test, so I put the negative sign. So this is our rejection region satisfying this equation. Okay. So this is our rejection region. And next, let's find the size n that satisfy this. Okay. So gamma of 19 is probability that theta equals 19. The reject the null hypothesis 20 over 3 over square root of n. Sorry. And is less than or equal to negative z 0.05, which is negative 1.645. And we want to make this 0.80. So if you solve this, you will see the n. So let's find the n, the sample size that satisfy the power. So from here, find n that satisfies this power. Okay, so this is probability that x bar minus 19 over, no. x bar minus 20 over 3 over square root of n is less than or equal to minus 1645 times 3 over square root of n. And if you make this is 19, we add 1, right? So we add 1. And we divide by the same number, this sigma part, x bar minus 19 over 2 over square root of n. So we divide it by 3 over square root of n minus 1.645 plus 1 over 3 over square root of n. And we want this to be 0.80. So if you look at the table, so let me see the table. .80. So we want this 0.80, so it should be 0.20. 0.20, the table tells 0.20 is 0.842. So solving this, let's see. So the equation says square root of n over 3 equals 1.645 plus 0.842, and then n is 3 times this guy and taking square. So let me use the calculator to compute this. So the number is 55.6665.2. So our n, the power is to satisfy this. So there is no, this is an integer, n should be an integer. So to get the roughly get this power, we will provide 55 or 56 to get this power. Okay. And any questions? Okay, and next. So it's a similar question and now, but here what's the difference? It is a little bit different question. So I'll give you 1 minute. See how can you solve this question. So it's about the sigma square. Think of the okay. So again, you have MP test, then you automatically consider the likelihood ratio theta 0, theta 1, which is, so we only consider the sigma square and the mean part is known. So the likelihood ratio 1 over 2 pi theta 1 square 2 pi theta 1 theta 0 square minus n over 2 e to the summation I equals 1 to n 2 theta 0 square xi square minus. Right? So this is the likelihood of the theta 0 2 pi theta 1 square minus n over 2 e to the minus xi square over 2 theta 1 square. So let me just take the log. So then minus n over 2 a log of theta 0 and taking this square and minus I equals 1 to 10 xi square 1 over 2 theta 0 square and plus n over 2 log theta 1 square and minus 2 theta 1 square I equals 1 to n xi square. This should be plus. Okay, so we consider the function of xi. So sum of xi square and 1 over 2 theta 1 square minus 1 over 2 theta 0 square. So if theta 1 is greater than theta 2, theta 0, then this is negative. So this is, we have the non-increasing emitter with respect to t of x equals sum of xi squared. So the most powerful test, so it's about the UMP one. So most powerful test, we didn't need to do that. Okay. So we don't need to MLR. Sorry about this. So when you talk about the MP, then we don't need to talk about the MLR. We just need that. We just say we are going to reject the null hypothesis. The rejection region with this ratio is less than or equal to something will be our rejection region. That will be the most powerful test. And here, I just removed the constant part in terms of x because we consider the rejection region, which is about x. And since this is negative, this is the same as sum of xi squared is greater than something. This will be our rejection region. Okay. And to find this critical value, we need to look at the test size, the significance level. So level is alpha equals 0.01. So let's find this critical value. And if you're looking at the n, so n is only 10, so which means we cannot apply CLT because it's not large sample. So we need to find the exact distribution. Okay. And here under H0, the sigma over sigma square over I equals 1 to n over sigma square, or x over sigma is normal random variable, standard normal random variable, just recall that. So summing this up to 10, it will follow the chi-square random variable. And the degrees of freedom is we add this 10 times. So chi-square 10 degrees of freedom. So under AC0, sigma square is 2. So our rejection region will be x. xi square 10, I equals 1 to 10, and sigma square is 2, is greater than or equal to chi square, so alpha 0.01. Okay. And chi-square 0110, let's look at the table. So the table, let me see. Chi-square 0.01. And 10 degrees of freedom. So it will be 23.209. So the test with this rejection region will be the most powerful test. Okay. Okay. Right. So that's it. So only the test. So it's easier question. And next question is also a similar question that uses the test the sigma square, but looking at the question. So here mu is unknown, and we want to test about the sigma square, and it's even more further. It's two-sided. So for this kind of question, there is no most powerful UMP test. So for this kind of question, we use the likelihood ratio test. And the question is exactly pointing that find the LRT. And assuming that n is large. So n is large, what we can get? When n is large, we can use the CLT, and furthermore, not even just CLT, we can use the asymptotic distribution of log likelihood here. So this is the LRT. Calculate the log likelihood and put the MLE. Then the theorem tells that this likelihood ratio times log likelihood ratio times -2 will follow chi-square distribution with k degrees freedom, where the k is the difference in dimensionality. It will be just 1 or 2 in most cases in this semester, right? So if you're testing sigma, then it will be just 1 will be the difference. Okay, so let's apply this. Okay, so LIT. So to get LRT, we talk about the LRT, we need to find the MLE on the AC0 and MLE in general. We need to do that twice. So in omega 0 or AC0, MLE. So there are two unknown parameters. So, two unknown parameters, mu and sigma squared. And we know the MLE for normal random variable. So mu hat sigma square hat is the x bar and 1 over n summation of xi minus x bar squared. And MLE under S is 0. What is the MLE for sigma squared under S is 0? What is the sigma 0? See, what is the MLE under S is 0? How about the sigma squared? So under SC0, yep. So there is only one possible values for the sigma square parameters. So this is one, and for mean value, you can easily see that the X bar will be the maximum likelihood estimate under the restriction SC0. Okay, and next, so first find this and calculate this, which is plug in the likelihood of theta z0 and plug in the theta hat MLE. That's all. So if it is too small, then we reject the null hypothesis. That is the LRT. So let's calculate this. 2 pi minus n over 2 e to the minus 1 over 2 x xi minus x bar square. Let me use the log likelihood. Sorry. Log likelihood ratio test statistic. So number is L theta hat 0 and L theta hat MLE. And looking at the log likelihood, so log minus n over 2 log of 2 pi minus 1 over 2 summation of I equals 1 to n xi minus x bar square minus plus n over 2 log of 2 pi sigma square plus sigma square hat and plus 1 over 2 sigma square hat summation of I equals 1 to xi minus x bar square, where sigma square hat is 1 over n summation of and xi minus x bar square. Okay, so given the data set x1 to xn, you can compute this, right? You can actually compute this if you have the xi's and x, right? X1 to xn, you can compute this. So this is our statistic, and we written as the log of lambda of x. So let me put just x. Right, so this is a function of x. And if you look at that, it might be complicated to find the distribution or find some part that has the monotone function of some non-distribution. So it is kind of complicated. So just consider this is our statistic. And we are going to reject if minus 2 log lambda of x, this x, this is a log lambda of x, is greater than something, because we are going to reject this is some smaller than something, and we are going to reject this if the log of lambda times negative 2 is greater than something, then we are going to reject. This is the rejection region in the log likelihood ratio test, likelihood ratio test. And assume n is large, it will follow chi-square distribution with 1 degree freedom, because the difference between the dimensionality of the parameters, the free parameters under null hypothesis, there's 1 difference. So it will follow the chi-square 1 degree freedom. So this k critical value will be chi-square 1 degree freedom, and the alpha equals just alpha here. Just alpha. So this is the critical value for this test. So it's kind of easier if you can assume that the sample size is large enough, then we can apply the symptomatic distribution of the log likelihood ratio in our t-test. Okay, any questions? Okay, then let's move to next example set. So in this set, there are some questions about the MLE, the MVUE. So let me briefly review these. Okay. So MLE, and actually it was also a part of our midterm exam. So I may not need to review this. Well, this case. So likelihood, we have the data set. And then likelihood of this, I sometimes use just data. Likelihood is just redefine the joint density function in terms of function of data. So when we talk about the density, data is given, the parameter is given, then this is a function of x. Density of this data set, right? However, when you talk about the likelihood, we consider this is as a function of data given the data set. So after the data set, we consider likelihood. So if the method use the likelihood a lot, then it's like a Bayesian approach. The philosophy is similar. You're considering the likelihood after you have the data set. So anyway, this is a likelihood. And for this is more complex compared to just addition. So multiplication is more complete structure. So we frequently use this take a logarithm. So log of likelihood. So we frequently write down in it as just x, or which indicates x1 to xn. Just follow the context of the problem. And then it's easier because we can rewrite this as a log of this. Right? And furthermore, if you divide this by n, you can see this is a form of weak log large number. So we can do something with this log likelihood. So it's easier because the likelihood itself is a form of multiplication of a function of IID data set. And if you take a look, this is just the addition of the function of the IID data set. So we can do something more with this log likelihood. And MLE is just, we are looking at the parameter that maximize this likelihood function. So that's all. So this is just optimization problem. We are looking for this on the parameter space. And this is the optimization problem. So if we have this likelihood function, very well defined likelihood function, the most frequently used technique is just solving this estimating equation, such that we differentiate this likelihood function in terms of data. Solving this equation, you will get we can write down this equation in terms of data. That will be your estimate. And then you need to check So it should be a form like that. This will be our theta hat MLE, and this is the L of theta, right? So theta hat MLE is the maximizer, which means you need to check that your second derivative, and just write it, is negative for all data that for the parameter space. So many cases you can find this MLE by using these two, checking these two conditions, but oftentimes some likelihood function doesn't satisfy this, or you cannot find this second derivative sometimes. So this is the basic part, and if you cannot do that, looking at, just consider how the likelihood function looks like. So you can find this as a maximum by checking like you can find this by L of theta. So this is L of theta. Now let me say this is theta something, and you can say that this is a maximum if your L prime theta is 0, is negative, is increasing. This is increasing when theta is less than theta 0. And this is decreasing when this is less than theta 0, for theta is greater than theta 0. So you can find the maximum like in this way. So these are another technique to find the maximum. Okay, so speciality. Okay, so this is the MLE, and MLE also have some very nice properties. Okay, and before that, you need to remember the information. So information, when we have one variable, information is expected value of theta. We are looking for the expected value of theta. The L, so L prime theta squared. Or it should be something like that. Okay, so if you have the IID data set, then your information will be so let me say this is I1. Let me define this as the information with one data or population. And this is information with this n data set is the same, but this should be a likelihood, the joint density of X. I forgot to write down this is log. So this is a sum of the log likelihood, right? So the inside of this square will be I equals to 1 to n theta of log at xi theta, right? And then if we use the fact that theta yes, expectation is 0. So if you use that, then this is just same as n times I theta. Right? So your information is added. This is like additive. As you have one more sample, your information is added, like added, and the amount of the information is the information from your first data set, the one data point. Okay. And it has by using this, you have the you can provide the lower bound for an estimate. So suppose the Rao-Kramer bound. So Rao-Kramer bound. So when we talk about the efficiency of the estimate, we consider the variance of the estimate. If the variance of the estimate is small, then which means your estimate is not very. It's not depending or it's not depending on the data set. It is very stable. So it has, which means it is more efficient estimate. So the Rao-Kramer rule bound is the variance of Y is, so Y is an estimate of K of theta. The variance of it is less than, its lower bound is K prime theta, and the derivative and square and Ni theta. So it's a lower bound. And if you consider theta, K of theta is theta, then you can see is K prime theta is just 1. So 1 over Ni of theta will be the minimum variance that any estimate of theta can have with the unbiased estimate. Unbiased. Okay. And MLE also have another property, the square of theta hat, MLE. So MLE have the asymptotic normality under a suitable condition, goes to normal distribution with 0 over 1 over I of theta 0. Okay, so this is the key part when you talk about the MLE. And so MLE. Okay, so let's do this. From the convergence, it's just for practice problem. So let the variable yn have a distribution that has binomial random variable and prove that it converges to something in probability to P. And don't apply the weak law of large number. So this part is actually the part of the midterm coverage. Okay. So let me see. Convergence in probability means that, so Xn convergence in some number X or C. So just write down just P, which means that for any epsilon, the probability that the difference between these two is greater than or equal to epsilon is always goes to 0 as n goes to infinity. Okay, so by using this probability, the uncertainty is expected out, and we want the convergence in probabilities. The difference between these two, the probability of this will goes to 0 if n is large enough. Okay, so we need to show that, so claim we need to show that to show the convergence in probability, we need to show that it's yn over n and p minus p. So for any epsilon, the probability of this guy, we need to show that this will goes to 0. And the Markov inequality or Chebyshev inequality, we can say that so yn minus p n over n minus p square over square, and this is less than or equal to the expected value of this over epsilon square, right? And yn over n is expected value is p, right? So it's basically the variance of yn over n. And so this is the variance of yn over n, which is 1 over n squared, the variance of the yn. And the variance of the binomial is npq. Right, so, and epsilon square p1 minus p equals to 0. Just for practice, I think one of the similar question was in homework or midterm. So just for practice. And let's talk about the MLE. So we have random variable, the discrete random variable. Oh, no, we have just table. Summary of a random sample of size 50 from a Poisson distribution. And we want to find the MLE of that probability that x equals 2. Right, so let's estimate this. Okay, how can you estimate? So in MLE, I forgot to mention that. So let me write down eta is a function of theta, a parameter, or a function of a parameter. The MLE of this eta is same as k of the MLE. And this can be actually, the proof is not that difficult. If you look at the definition of the MLE, yeah, if you look at definition of MLE, so if you're looking at the definition of MLE, this is not that difficult to prove. So if the parameter is a function of a parameter, then the MLE of this parameter is a function of the parameter, the function of the MLE. So we can keep this function. We can keep this. We only change this inside. And if you're looking at the question, the final question is we want to estimate this. So let's rewrite this in terms of the parameter that is familiar to us. So the PDF says is e to the minus lambda, lambda to the x factorial. It's definitely a function of the parameter. And if so we can easily see that if we can find the lambda head MLE, then we can find the MLE for this. It is just e to the minus lambda MLE, lambda head MLE square over 2 factorial. Okay, so this is just plugging in. So the key is find this lambda hat MLE. So let's find this. So here we have the, how many? There are total 50, and the likelihood, and then L lambda, the log likelihood is minus n lambda and plus sum of xi log lambda minus log xi factorial. We want to find the lambda that minimize this, so you can easily figure out lambda hat MLE will be x bar. So this procedure you need to check by yourself. So this is just a simple computation, checking the derivative. So I'm not going to do this in this class. You can do this by yourself. So we get the MLE, then just plug in over there. And before plugging in, the question is asking us to provide the real number. So we need to find the x bar first. So sample mean is just the sample mean. So weighted sum of x. So out of 50, 0 times 7 plus 1 times 13 plus 2 times 11, 5 times 2. Right, so x bar, what is the x bar? It's 2.5. Then our MLE is e to the minus 2.5, 2.5 squared, 2 factorial. And just put the numbers into your calculator and you get the answer. Okay. Right, next. So this is about the MLE question. And in addition, this asking show that it's efficient. So efficient of an estimate, when you see this, you need to consider the variance of the estimate. And efficient means that the variance of the estimate it achieves the minimum variance that the estimate can have, right? So which means it achieves the Kramer law lower bound. That's all. Okay, so let's see the question. The first, find the MLE. And next, let's compute. We're going to compute the variance. And next, we're going to check the Kramer law lower bound. And if it achieves this lower bound, we say that it's efficient. Right? Let's first find the MLE. So I'm going to skip the procedure of finding the MLE. You can find the examples of this non-random variable in the slides, and we already did in the class. So you just calculate the log likelihood and taking derivative and make it equals 0 and get the solution and check the second derivative is less than 0. So that is, it achieves the maximum. So that's all. And then you will see that theta hat MLE is a theta of the variance part will be 1 over n sine squared. Okay. And the variance of it. So X are normal random variable, and variance the variance of their head is 1 over n summation of I equals 1 to n xi squared. So 1 over n squared, and xi's are IID. So the variance of summation of n times variance of xi, the variance of x1 squared, and x1 squared, and if it is square with chi square 1 degrees freedom, and gamma 1 over 2, the variance of chi square 1 is alpha beta square, so 2. So variance of x1 square is, so variance of x1 square over theta square was 2. So variance of x1 square will be 2 theta square. So we will get 2 theta square over n. This is the variance of the MLE. And next, let's check the CR lower bound, so Kramer lower bound. So to do that, we first find the I of theta, the information. The information is expected value of the information. This guy. So we anyway need to find the log likelihood. So let's just calculate the log likelihood. So theta so in this Kramer lower bound, so this I of theta is computed by using one component. So I'm going to calculate this information for the one component. Okay. So for a single normal random variable, this the likelihood is minus log 1 over 2 minus 1 over 2 log 2 pi theta minus 1 over 2 x square over theta square, no, theta. Oh, I made a mistake over here. Theta is the variance, so I need to write them like that, right? X over square root of theta will standard normal random variable. So I made a mistake. I need to remove this. Okay, then I should remove this square. So anyway, so and take derivative. Minus 2 theta, right? Plus 1 over 2 x squared theta squared. So expect the value of, I'm taking square. Ooh. Oh, so instead of using this, we know that this is the same as expect the value of minus the variance of, right? So we have some property regarding the information. Yeah, it's sometimes annoying to compute this. So by using the expected value of this first derivative of log likelihood equals 0, so we use this. I'll double print there. Okay, so you may remember this property. Taking the derivative again. Okay, so the another derivative. Two theta squared and minus 1 over 2 minus theta to the negative 3 x to the 2 theta to the 3. Okay, and the expected value of L double prime theta is minus 1 over 2 theta squared plus expected value of x squared over theta to the 3, and expected value of x squared is theta squared, so this is minus 1 over 2 theta squared plus theta, so theta over theta to the 3, so this is 1 over 2 theta squared. So is it right? Okay. Okay, so our information is this 1 over 2 theta squared, and Kramer-Rao lower bound for the variance is ni theta, so 1 over 2 theta squared over n. So this is the lower bound. And now, oh, this is theta. What happens? Oh, the mistake is over here. So variance of x1 square over theta equals 2, which means the variance of x1 square is 2 theta squared, right? 2 theta squared, sorry. So the variance of this MLE achieves the Kramer-Rao lower bound, which is 1 over ni theta. So this theta hat MLE is an efficient estimate. Okay. So in the next class, I'm going to review this some more questions, and we'll finish this lecture. And yeah, just email me or yeah, any questions about these courses, lectures, or exams. Okay, then let me stop here and see you Thursday.